Well, thank you guys for having me here today. It's been great. It's good to be in Boston. And so we've seen some incredible manufacturing technology, but I'm going to talk about software. I started nTopology about 3 years ago with the goal of making a more intelligent CAD system. And so we've seen, from Desktop Metal, Markforged, amazing manufacturing technology. But if you look at the actual design software, there hasn't been as much investment in new design software. And CAD really has kind of stagnated over the last, let's say, even 30 years in some ways. I might get in trouble for saying that here, but when you zoom into the product design process, you have this intricate web where CAD is separate from both the computer-aided engineering and simulation and manufacturing setup. And the CAE and CAM is really not connected to your design process. And so if we look into CAD a little bit closer, the dominant force in CAD over the last 30 years has been parametric design and parametric modeling, right? And even the kind of newest CAD systems today are still built in parametric. And so what we're trying to do is drive the future with generative design, right? And so we see, whereas the kind of industry standard being feature-based modeling, we think the future with generative design is functional modeling, right? And so I can kind of go in with our process. With functional modeling, it's an interesting term because it's like a double entendre. On one hand, the functions drive the part, the function of the part drives the design, but on the other, you're actually tiling together these independent functions to create your part, right? And so in our process, you can start with the design constraints, right? In this case, it's a pressure vessel. I have the part at our booth. And with the pressure vessel, it's a pressure vessel that has to be round to elliptical to round. And then you can come up with a design rule. So in this case, we wanted a rib structure. So you can program a rule that can have, variable height, variable thickness, variable offset. And then you compile this functional graph. And so whereas in parametric and feature-based, you have this linear history, you have a sketch that's driving a feature. With functional modeling, you can tie together independent functions to create reusable parts. Like you can take a rib structure from that pressure vessel and then apply that same rule to like a airfoil or a wing. And so we released the first version of our product February 6th of this year. You guys can download a free version, and then we also have a pro version. And it's being used in the real world today as well, both in aerospace, footwear, etc. And so I'm going to talk a little bit about the kind of geometry and topology that we're using. And so we have two main data types that we've kind of introduced that are different than a traditional boundary representation. A graph and a narrowband level set. And they both give us ways of representing data at different levels. So the graph basically gives us a set of nodes, connections between those nodes that can be linear beams or shells. And then we also have this volumetric representation, which is the narrowband level set. And so the graph allows us to represent really complex lattices based on the kind of medial axis, right? You can represent the middle surface, and then with attributes, you can apply thickness to get your final part. But then the narrowband level set is a volumetric representation, and which allows us to do like really clean booleans and unions while maintaining a really nice hard edge between parts. And so what we use to drive these structures are modifiers. We can make a modifier with kind of stress values, or we can make a modifier based on the distance to geometry. Things like the distance to a point, the distance to a surface, the distance to a line, etc. And so this is a kind of simple bracket, and you can see the effect of the modifier. In this case, if I want to make a structure that kind of gets thicker around the mechanical connections, I can set up a modifier to say, okay, give me the distance from all of these mechanical connections. I can kind of affect by changing the fall off or the graph for the fall off from those mechanical connections to kind of change the distance if I want. And then I can fill that structure with the lattice based on that rule that I ran, right? And you can kind of see with the section that gradient. In this case, we're using that volumetric representation to extract a clean gradient surface from the part while maintaining those mechanical features. And you could also apply the distance field based on the graph, right? The graph, we can represent even more complex structures because it's a little bit lighter weight. And then we can change, and still, again, we can combine, go from graph to volumetric, volumetric to mesh, CAD to volumetric, et cetera. So you can still have kind of, boundary representation where you want clean mechanical features, but then you can have the graph for the lattice. And so there's a couple example, let's say, classes of parts that you can kind of set up these rules around, right? So first thing I'm going to go into is ribs, right? And so this was a pressure vessel that was for a rocket part. And the goal was basically to create this, to kind of minimize the distortion of the pressure vessel. I have a couple example parts here. And so, if you're making rib parts, in this case, we reduced the deflection 27x just by adding ribs compared to the single surface, right? Similar concept to having beams on a floor. Then we can also create more optimal structures, optimal direction, optimal thickness for ribs. And that this is one of the final parts. Now, again, with these ribs, you might want to take into account mechanical features, right? And so in this case, instead of having ribs throughout the whole part, maybe only on the up skins you want to have ribs. And that's another kind of change in the graph, and say, okay, instead of having my modifier be the distance to the two edges, you can have the modifier be the angle of the surface. And so here's kind of another simple, flange. And if I'm going to make ribs on this flange, there's a couple ways we can do that, right? And so, the first one would be, let's just cover the surface and trim the edges, right? And so you kind of get this pattern that gets cut off on the edges. It's not so nice, right? And so maybe as an alternative, you would want to make a conformal structure. And so in this case, you can take the surface parametrization, map that surface from 3D to a plane and build the ribs that way. And again, so this is our conformal structure module. And so, you can change the size based on the parametrization to have different size of ribs. You can have lots of ribs. And then for thickness, again, you could use a modifier, right? So you can use the distance to the edge. Maybe you want these ribs to be much thicker, closer to the edge. And you can drive parameters of parts of the geometry with these distance fields, et cetera. Now, if you want the ribs to be optimal, so we have a new module that's coming out for our topology optimization, you can set up a set of boundary conditions. So this part happens to have a torque on it. And so we went ahead, applied a few loads to the part, fixed the bottom. And so this is based on these Mitchell truss structures. It's kind of what's the optimal structure that you can get based on a specific loading condition. And so the output happens, in this case, to look kind of like a clover that we get from that. And again, both the orientation is being driven by the topology optimization, and then we're changing parametrically the thickness and height of the geometry to fulfill that specific loading condition. And then we can also drive cellular structures, right? And so with cell structures, we can do like simple gradients in the cell structure based on these modifiers, right? You can have kind of more functional parts, again, maintaining those mechanical connections. Another control arm. And you guys can see this brake pedal also at our booth.